Pushing through now on number 20, we do want to make it less than 16.5 years old, not older than, but less than 16.5 years old, okay? Group 625 students, mean age of 15.8, so there's your mean. Standard deviation 0.6, got that. Ages are normally distributed, okay, I'm thinking normal CDF here. What's the probability? Randomly select one. I'm not looking for central limit theorem here. So you want to be less than 16.5, so therefore I'm going to go from negative 10 to the 99th all the way up to 16.5. So that's my lower and my upper. 15.8 is my mean and 0.6 is my standard deviation. Punch the numbers in, 0.8783. Number 21 is a great exercise as a study tool for your final exam because you've got one in part A where it's less than, one in part B where it's between two values, and one in part C where it's more than. And if you can do this one and the other ones that we have on here, no matter how I word it, no matter how I tweak it, whether it's central limit theorem or this, and you know these bounded intervals, you are in great shape. So all of these obviously are going to begin with second bar's normal CDF. If you're less than 40,000, you're from negative 10 to the 99th up to 40,000. If you're between 45 and 60,000, you have the lower 45,000, the upper 65,000. And if you're more than 70,000, you start with 70,000, you go up to 10 to the 99th. And then you crunch all those numbers and pop it all out. For the first one, it comes out to be 0.3085. For B, it's 0.3721. And for C, it's 0.1587. Now, notice the difference. Here, we're looking for what percent of the people earn less. Or in the previous one over here, it's what's the probability of randomly selected single individual student. When we look at number 22, it says the population mean annual salary. Okay, that we can work with. Starts talking about random samples of 49 plumbers, and then it starts talking about keyword magic word here. Mean salary, magic with this mean salary. That means we're going to go central limit theorem, and what that means is our adjustment, you got to take the standard deviation and divide by the sample size, in this case 49. So, second bar's normal CDF, the minimum value is 47,300. Then you go to the maximum value, which we represent with 10 to the 99th. And then you go a mean of 49,300. And we already talked about the standard deviation. You got to do that, 5,500 divided by the square root of 49. Crunch the numbers, 0.9945. Okay. I almost forgot to do a t-test on this one, so I almost caught myself making a mistake. And I always do something stupid. It's one of my problems in life. Okay, next up, 90% confidence level for Toyotas. So I put these Toyota values into L1. Okay, remember how you do that? You go to stat and then data right away, edit, you put it in there. Once you put all of those values into L1, you go to stat t-test, which is stat test to the 8th one down. You don't even see it on the first screen. You got to scroll one past. It'll say T interval. The input goes from the data. The list is L1. Frequency is 1. And the confidence level is 0.90. Punch those in. It'll tell you 30.113 to 33.576. Okay, number 24 talks about a group of 25 rats, and you're selecting that group of 25 rats, which means there's other rats. And when you select it from the other total population, you now have created a sample. 25, null and alternative hypotheses for the situation described below. Particular compound in drinking water is not hazardous if it's present in 27 parts per million or less. So the null is that the a watchdog group believes it's actually more than this. So the null is that the compound is less than or equal to 27. Remember, all equals always go with the null hypothesis, and the alternative is that it's greater than 27. Okay. Number 26, what does a p-value represent? Always represents probability. That's why we use the letter P. What are the smallest and largest p-values? Well, it's a probability. So the smallest value is 0, and you can equal 0, so it's less than or equal to, and the largest is 1, less than or equal to 1. For this problem here, for some reason, they didn't have a standard deviation listed, so I went with 2.5. And we want to find a confidence interval. So I do 1 minus 0.9 because it's a 90% interval. That's 0.1. Divided by 2, you get 0.05. Then I got to do second var's inverse norm to see what it is that's on both ends of the normal curve, that white area we learned about in class. I get negative 1.6449. So I just used the positive version of it to find my error bound. 1.6449 times the standard deviation, which is 2.5, over the square root of the sample size, which is 200. When I multiply that, the product is 0.2908. And then I take the mean, which is 7.4, and because that's the middle now, and I subtract the 0.2908, and I add the 0.2908. And that gives me 7.1092 and 7.6908. And that is my 90% confidence interval. Number 28, conclusions should reference accepting and rejecting the null hypothesis. Suppose our p-value is 0.074. How will it be affected by alpha levels of 0.10, 0.05, and 0.01? So for 0.10, the alpha is greater than the p-value. So p is low, the null must go. If I use an alpha value of 0.05, p is greater than the alpha. So if the p is high, the null must fly. And if p is for the 0.01, if it's greater than 0.05, it's going to be greater than 0.01. So if p is high, the null must fly for both of those. Okay? Now, we're getting to next, we'll pick up in a minute.